Hello again, everyone. In this lecture video is going to be the second in a two-part series on standing waves. So if you haven't watched part one, where I talked about standing waves, go back and watch that first. And then in this part, I'm going to continue where I left off with that one. So basically, just to remind you what the purpose of this lecture was to talk about what a standing wave is and how to represent it mathematically. And this is what was discussed in the previous part. So what I want to talk about in this remaining part is about standing waves on a string with both ends fixed, or in a pipe which has one or both ends open. And those are, the applications of that are, of course, string instruments and wind instruments. We want to talk about which frequencies can a string vibrate at if it has both ends fixed, and similarly, which frequencies can air vibrate at in a pipe if I have one or both ends open. Okay, so why is a string with fixed ends interesting? It's interesting because it makes sense how to fairly easily generate a standing wave in this case. So we've talked before about what happens when a wave encounters a boundary. So in this diagram at the top of this slide here, this end of this string is fixed to the wall, and if you send a pulse down the string, it will be reflected back upside down when it hits that boundary. And this is something we talked about in previous lectures. So in the previous video, we talked about how a standing wave is formed by having two waves traveling in opposite directions interfering with each other. So you can see how you could make a standing wave. You just send a pulse down the string like this by wiggling your hand up and down in a sinusoidal motion, and then wait a little while and send another pulse down the string in a sinusoidal fashion. When the first one gets reflected backwards, now I've got two sine waves traveling in opposite directions, and when they pass through each other, I'll have a standing wave. Okay. So it turns out that if you wiggle your hand at exactly the right frequency, you will get a standing wave which has this end being a node and this end being a node. Right? And that's what you need, because if the two ends are fixed, you need the ends to be nodes. Okay? So that's the key point when I'm talking about a string which is fixed at both ends. So just like a violin, I've got one end of the string fixed and the other end of the string fixed. If I can set up a wave in that string, a standing wave, that standing wave has got to have the ends being nodes, because those 2 points which are fixed can't move at all. And we know that the nodes are half a wavelength apart. So that means the length of the string between one fixed end and the other fixed end, the length of the string has to be some multiple of half the wavelength, because the nodes are half a wavelength apart. And so I need to have an integer number of half wavelengths fitting into the string. So L is the length of the string. It has to be divided evenly into some multiple of half wavelengths. This is the condition for standing waves if both of the ends have to be nodes. So lambda n is going to be the wavelength of the nth standing wave. It's going to be 2L divided by n. And n is some number, integer number, 1, 2, 3, 4, so on, like this. We call this n the harmonic, the nth harmonic, okay? And the key thing to remember what the n stands for is that nth harmonic has n antinodes. So it's the number of antinodes, basically. Okay? Hopefully this makes sense. I'll show some pictures in the next slide. So if I start with this condition, knowing that the length of the string has to be evenly divisible by half wavelengths, I can also think about what frequencies I need to joscillate the string at in order to meet that condition. So remember, we know that lambda n times fn is equal to v, right? So fn is equal to v divided by lambda n, which is v divided by 2L over n. And then if I put the n in the denominator here, the 1 over n in the denominator in the numerator, I end up with this formula down here. So v is the speed of waves on the string. That doesn't change, right, assuming I don't mess with the tension of the string or anything like this. And this tells you which frequencies I can oscillate the string at in order to get a particular standing wave. So here are some pictures of standing waves on a string with both ends fixed. So you can see here, both of the ends have to be nodes because those places are fixed and so they can't move. The lowest possible vibration I can have is to have one antinode in between the two nodes, right? So remember, n is the number of antinodes. So if n is equal to 1, I have one antinode halfway between the nodes. And then this, what's the wavelength here? Remember that this is only half the wavelength, right? The other half would have to be drawn on the other side like this. So that means that the length of the string in this case is 1/2 of the wavelength. If I jostle the string a little bit faster, I could set up a standing wave like the one shown at the right here. Again, the ends are nodes. So this is a node, this is a node, but now maybe there's a node halfway between. And then I've got two antinodes. So that's n equals to 2. Okay. What's the wavelength here? Well, the wavelength, if I look at one snapshot of the string, is like this. The wavelength is in fact the whole length of the string. Remember, this distance here is L. So L is the length of the string. And so in this particular situation, the wavelength is L, okay, and n is equal to 2. And then you can imagine sort of how this goes on. Then maybe the third one, I've got 3 antinodes, n equals to 3. So I've got 3 antinodes, 1, 2, 3, like this. And what is the wavelength? So the wavelength here is there. Okay. You can see that lambda is 2/3 of the string length. Or if I rewrite that, it's this, right? Lambda is 3/2. Or sorry, L is 3/2 times the wavelength. So hopefully you're seeing examples of this particular formula, which I mentioned on the previous slide. The length of the string is divided into an integer number of half wavelengths. So if n equals 1, I've divided it into 1/2 wavelength. Right? So there's 1/2 wavelength and 1 antinode. If n equals to 2, I've got 2/2 wavelengths, which is a full wavelength, and 2 antinodes. If n equals to 3, I've got 3/2 wavelengths and 3 antinodes. Let me try to illustrate that with a simulation. Okay, so here we go. I've set up the string here to be oscillating with a very low amplitude and some frequency, and I've set this end to be fixed. Let me get that thing going. It's going to take a moment. Let me put it in fast motion for that standing wave to develop. You'll see that I have chosen these parameters such that I am getting a standing wave. Okay. So now that it's being developed, let me put it in slow motion so you can see it. Okay. So hopefully you see I've chosen the numbers such that the green dots are nodes. And so the end is a node, and there's another node, another node, another node, and then here's the antinodes halfway in between the green dots. Okay. Right. So this is clearly one of those standing waves with a frequency of 2.5 hertz. That's the frequency at which I oscillate this thing. Okay, so this clicker question, simple question, what frequency would I need to drive it at to reach the second harmonic? Okay, so I took a screenshot. This is a screenshot of one of the particular, of the one I just showed you. Remember, the one I just showed you had frequency 2.5 hertz, and the green dots were nodes. Now my question for you is, which one of these frequencies would I need to drive it at to reach the second harmonic, which is n equals to 2? Try and work it out. Pause the video. See if you can come up with an answer to this question before going forward. And once you're ready, unpause the video. Okay. So the first thing to think about is, what is the value of n in the one that I just showed you? Remember, n is the number of antinodes, right? So how many antinodes do I have in this one that I just showed? Let me put it in motion again. Okay, here's 1. Here's 2. Here's 3. There's 3 antinodes. 4, 5, 6. This is 6 antinodes here. So this is n equals to 6. So this one down here is n equals to 6. Now the question is, what do I need to change about it if I want to reach n equals to 2? the formula that we're looking at is this one, right? Now V is fixed. I don't change the tension of the string or anything, and I don't change the length either. So the only thing that I have is that the frequency is proportional to n, right? So my initial frequency, F initial, was 6V over 2L. And I want my final frequency to be 2V over 2L. I want n to be equal to 2. So it makes it clear that if I want my value of n to go down by a factor of 3, I need to decrease my frequency by a factor of 3, F initial divided by 3. So the answer to this one is 0.84. I started at n equals 6. I want to end up in n equals 2. The only way to do that is to decrease the frequency by a factor of 3. 2.5 divided by 3 is about 0.84. Let's try it out. So let me decrease this now to 0.84 and restart it and give it a second to develop. You'll see here that the n equals 2 pattern is showing up. I'm getting 2 antinodes. So you're seeing here's the antinode here, and here's the antinode here, and this point in the middle is the node. This is n equals 2. I got it by decreasing the frequency by a factor of 3. Hopefully you can see, like, what if I want n equals 1? I should just divide this in half. So n equals 1 would be 0.43. 0.42. So if I let this go, it's a little bit slower, but starting to happen. You can start to seeing this is the n equals 1 harmonic, right, where I have one antinode and then 2 nodes at the ends. So you see there's only these specific frequencies which lead to the standing waves. So 0.42, 0.84, 2.5 was another one. But if I just move it at some random frequency, I won't have a standing wave like that. Like, what if I put it at 1, which is neither, that's not one of those special resonant frequencies? What's it going to look like? You can see the string will move, but it's not forming that nice standing wave. It's kind of just not doing much. Okay, so there's only those special frequencies which lead to the standing waves on the string. If you play a string instrument, you have exactly this situation where both ends of the string are fixed. So one is fixed here and the other one is fixed up here. And you're getting that thing to vibrate at certain frequencies. Now it turns out when you pluck the string, you're hearing a combination of all those different harmonics. So actually, you're hearing both n equals 1 and n equals 2 and n equals 3 and n equals 4. You're hearing a combination of all those harmonics. We call them overtones in music. You can change the note that you're hearing by changing the length of the string. That's why when you're playing the violin, you move your finger up and down, and that's changing the length of the string, which is changing this frequency that you're hearing, right? If I change L, then the frequencies that are allowed are going to be different. You can also change the frequencies by changing the tension in the string, and that affects the velocity of the waves, right? So you know that when you're tuning an instrument, you're tightening the string or loosening it, and that is going to be changing the allowed frequencies, which you will be able to hear when that string vibrates. Here's another clicker question. Suppose a standing wave on a string vibrates as shown, so that's this one here. Now you reduce the string tension to 1/4 of its original value, but everything else is kept unchanged. Which standing wave pattern will be produced? Pause the video, try and work it out yourself, and once you have an idea about which one you think is correct, come back and we'll work it out together. Okay, so my original standing wave here is n equals 2, right? I have 2 antinodes, n equals to 2. Now what happens when I change the tension? The string tension is reduced to 1/4 of its initial value. What does that affect? Remember, the speed of the wave on a string is square root of t divided by mu, right? So if I substitute that into my frequency, it's going to be it's going to be n over 2L, square root of the tension divided by mu, okay? So initially, I had n equals to 2. So let's do the following thing. F initial will be n initial over 2L divided by the square root of the initial tension divided by mu. Okay, mu and L don't change, so I don't need to say initial and final. And then F final will be the same thing. N final over 2L, square root of the final tension divided by mu. Now let's take the ratio of those two. What is F final over F initial? I'm going to have N final over 2L, square root of T final over mu. And then on the denominator, I've got N initial over 2L, square root of T initial over mu. Everything cancels except for the n's, because the n's might be different. So the 2L's are going to cancel and the mu's are going to cancel. So what do I get here? F final over F initial is going to be equal to N final over N initial times the square root of T final over T initial. Okay. But it says that the frequency and length are kept unchanged. Okay. So that means the left side is equal to 1. So the final and initial frequencies are the same. N final over N initial. And the tension is reduced by a factor of 1/4. So the final tension is 1/4 of the initial tension, like this. So this I can solve for. I get N final is equal to 2 times N initial. And so if my initial standing wave was 2, N equals 2, this one would be N equals to 4. And so this would be the one which we will see. Okay, so the answer to that one is C. The wave speed decreases by a factor of 2 because, the speed v depends on the square root of the tension. So if I decrease the tension by a factor of 4, the speed decreases by a factor of 2. That means n has to go up by a factor of 2 in order to keep f the same. Okay, and then you can do it with the algebra shown here. Last thing I want to talk about is standing waves in air columns. So not in a string, but let's talk about standing waves of sound, which you can create in a pipe. You can cause the air to oscillate in a standing wave. And it works the same way. If this end is closed, you can send a sound wave down this way and it would reflect back. Okay, the key point is that for a string, which is fixed at both ends, the ends both have to be nodes because they can't move. Okay. When it comes to sound waves in a pipe, if an end is open, that's an antinode. Okay. Open is an antinode, and to be precise, it's a displacement antinode. What it means is that the molecules are moving the most at the open end. So the open end will be an displacement antinode, and the closed end will be a displacement node because it makes sense that if the end is closed, like here, the air molecules can't move anywhere because they're just up against that wall, so they can't, go anywhere. So you have a little bit of a different situation. If, for example, what I'm drawing here is a pipe which is open at both ends. So if both ends are open, they each have to be antinodes. Okay, so notice on this end I've got here an antinode because this is an open end, and this is also an antinode, open at both ends. This is both open at both ends. That's n equals to 1, and then this is n equals to 2, again antinode at both ends, and this is n equals to 3, antinode at both ends. You see that the condition is exactly the same as for the wave on the string. Lambda is 2L in this case, lambda is L in this case, lambda is 2/3 of L. So it's like all of the same frequencies are present as with the wave on the string fixed at both ends. The only difference is that for the wave on the string, the ends were nodes, but for this one with the pipe open at both ends, the ends are antinodes, but the same frequencies are present. It gets more interesting if you start to close one end and open one end. Okay. So what if I have this situation where the right end is closed? remember the closed end is a node, so the molecules can't move. So here's a node at this end. The right end is closed in this case. But the left end is open, so the left end has to be an antinode. So here's an antinode here, antinode, antinode. So you have different situations here. If I have the left end being an antinode and the right end being a node, the lowest frequency which would allow for that is the wavelength being 4 times the length. Remember that the distance between the node and the antinode is 1/4 of the wavelength. So this has to be lambda over 4, distance between a node and an antinode. So L is equal to lambda over 4 for this first harmonic if one of the ends is open and one of the ends is closed. The next one that you could have is you could have a node in between. So I've got to have one end being a node, one end being an antinode. I could have one node in between. And this distance here is 1/4 of the wavelength. And then this is half the wavelength, right? So the total that I have here is 1/4 plus 1/2, which is 3/4 of the wavelength. So L, in this case, is 3/4 of a wavelength, which you can see agrees with this equation that I wrote here. Lambda is 4/3 L. And then you could do the same thing again with the one at the bottom. So this is going to be 1/4 plus a whole wavelength, right? So here L would be equal to 5/4 of a wavelength. You see, the ones that are allowed, the frequencies which are allowed are different if I have one end open compared to if I have both ends open or both ends closed. So let me try to summarize that. On the left side, I've got open at both ends. And this formula for the allowed frequencies for the standing waves is the same as the one we saw before, NV over 2L, for the string fixed at both ends. Okay, N is 1, 2, 3, so on. Okay, so really nothing that surprising here. But if one of the ends is open and one is closed, I have a different set of frequencies which are appearing. Right? So the first one that appears is V over 4L. The second one that appears is 3V over 4L, which is 3 times the first one. And the third one that appears is 5V over 4L, which is 5 times the first one. So if one end is open and one end is closed, you have a different set of frequencies which lead to the standing waves. Fn, sorry, this should be an M, just to be clear. Fm is equal to mv over 4L, and m is a number, an odd number, 1, 3, 5, 7, 9, so on. So basically, if one of the ends is open, only the odd harmonics are present, and there's no even harmonics. Right? So these formulas are straightforward enough to use. The challenge here is just to remember, when do I use which one? Under which circumstances do I use which one? For a string with both ends fixed, I have this equation. If a pipe is open at both ends, I also have the same equation. But if a pipe has one end open and one end closed, I have a different equation, and I have different frequencies which lead to standing waves. Okay, in particular, only the odd numbers are showing up here, and I have a 4 in the denominator instead of a 2. The standing waves in air columns, the applications are instruments. A pipe organ or a pan flute has both ends open, and so you have a different set of frequencies which are present. Let me summarize this big important topic of standing waves. So I mentioned this from the last video. If you have two waves of equal frequency and equal amplitude traveling in opposite directions, a standing wave is produced. If you have a standing wave on a string which is fixed at both ends, you can create a standing wave there by sending waves down, and they get reflected backwards, and you get that interference that you need. These places where you have no motion are called nodes, and the places where you have the biggest amplitude of the harmonic motion are called antinodes. If you're going to have a standing wave on a string fixed at both ends, the ends have to be nodes, and that means that because the nodes are half a wavelength apart, I have to have the length of the string being evenly divisible into half wavelengths. that led us to this condition here. Lambda n is 2L over n. The same thing is true if you have a sound in a pipe with both ends closed or with both ends open, because then both ends have to be nodes or both ends have to be antinodes, and in both cases, the distance between those is a half a wavelength. So all of the above situations here, you have the string fixed at both ends, you have the sound wave in a pipe with both ends closed, sound wave in pipe with both ends open. All of those situations will have the following frequencies will lead to standing waves. On the other hand, if you have a situation where you have a string which is free in one end and one end fixed, the fixed end is a node and the free end is an antinode. And this also happens in a pipe which has one end open and one end closed. The closed end is the node, the open end is the antinode. And in these situations, you have a different formula for your standing wave frequencies. mv over 4L, and m takes on the odd numbers, 1, 3, 5, and 7. Okay, so now you know you understand what a standing wave is, you understand the formula for the standing wave, and you understand the conditions for the what are called resonant frequencies, which frequencies will lead to a standing wave on a string which has both ends fixed, or one end fixed and one end free, or both ends free, or in a pipe which has one end open, one end closed, or both ends open. Thanks for your attention, and I hope you found this lecture useful. See you all in class, and bye for now.